Welcome back to our lecture series on nanostructured materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In this lecture, we will explore crystal structures, starting from the basic definition of crystals and unit cells, moving to Bravais lattices, cubic systems, packing, and ending with magic numbers and nanoscale effects. This knowledge is essential for analyzing nanomaterials because their small size often modifies or distorts classical crystallography. Why do we study crystallography at all? The reason is simple. The atomic arrangement or crystal structure largely determines a material's properties. Consider carbon. In diamond, carbon atoms form a three-dimensional network of covalent bonds. This gives diamond its extraordinary hardness, high thermal conductivity, and transparency. In graphite, the same carbon atom arranged in layered sheets with weak van der Waals forces in between. This results in a soft, slippery material that conducts electricity. When those sheets are peeled down to 1 atom thickness, we get graphene, a two-dimensional hexagonal lattice known for its exceptional electrical conductivity, flexibility, and strength. The same element carbon shows radically different behavior simply because of structural arrangement. The same principle applies to metals, ceramics, and semiconductors. Whether an alloy is strong or weak, whether a ceramic is tough or brittle, or whether a semiconductor absorbs blue light or red light, all depend on underlying crystallography. That is why we must carefully study lattice structures before discussing nanomaterials. At the simplest level, we can think of a crystal as a solid in which atoms are arranged in a repeating pattern. This captures the idea of long-range order. However, to be more rigorous, we describe a crystal as the combination of two elements, the lattice and the basis. The lattice is a set of mathematical points arranged periodically in space. The basis is the actual atom or group of atoms that we attach to each lattice point. When the basis is just one atom, the structure looks like a simple repeating array of spheres. But the basis can also be more complex. For example, in sodium chloride, the lattice points alternate between sodium and chlorine atoms. Therefore, the formal definition is crystal equal to lattice plus basis. This distinction is important because it allows us to describe both simple metals and complex materials with the same language. While crystals extend infinitely in 3 dimensions, we don't need to describe every atom individually. Instead, we use the concept of a unit cell, the smallest repeating building block that captures the full symmetry and arrangement of the structure. By stacking these unit cells along the 3 lattice vectors, we can reproduce the entire infinite crystal. Think of tiling a floor with identical tiles. Each tile represents a unit cell and the floor represents the crystal. Importantly, there can be multiple ways to define a unit cell, but crystallographers prefer the smallest, most symmetric one called the primitive unit cell. Sometimes, for convenience, we use larger non-primitive unit cells if they are easier to visualize. Understanding the unit cell is crucial because its dimensions, known as lattice parameters, are measurable experimentally. For example, through X-ray diffraction, and directly relate to density, packing, and material properties. Essentially, the unit cell is our window into understanding how atoms are arranged in crystalline solids. Although atoms could, in principle, arrange in countless ways, mathematics shows there are only 14 distinct three-dimensional arrangements that repeat periodically. These are known as the Bravais lattices, after Auguste Bravais, who formalized them in 1850. Each Bravais lattice is a unique way to fill all of a space with points in a repeating pattern, without gaps or overlaps. What makes this classification so powerful is that no matter what crystal we encounter, a metal, a ceramic, or a semiconductor, it will always correspond to one of these 14 lattices. For practical use, these 14 lattices are grouped into broader families called the crystal systems based on their unit cell geometry. In the next slide, we will look at those 7 systems in detail, defined by their edge lengths and angles. But it is important to keep in mind that the Bravais lattices remain the most complete and fundamental classification of three-dimensional periodicity. Now that we know there are 14 unique Bravais lattices, let us step back and see how they group into 7 broader crystal systems. These systems are defined purely by geometry, specifically the relationships between unit cell edge lengths and angles. The cubic system is the most symmetric with all edges equal and all angles 90 degrees. If we stretch the cube along one axis, we get a tetragonal system where 2 edges remain equal but the third differs. Orthorhombic cells still preserve 90-degree angles, but now all 3 edges are unequal. In the hexagonal system, 2 axes are equal and meet at 120 degrees, with a third perpendicular axis. Monoclinic system relax one angle away from the 90, while triclinic system have no right angles at all, representing the least symmetry. Finally, rhombohedral or trigonal cells have equal edges but oblique angles. This classification gives us an elegant way to visualize and categorize crystals by their fundamental shape before diving into packing or symmetry details. Once atoms are arranged in a lattice, a natural question is how many neighbors does each atom touch? This is called the coordination number. It is a measure of local atomic environment and it strongly influences material properties. For example, in simple cubic, each atom has 6 nearest neighbors. In body central cubic, that number rises to 8. In face central cubic and hexagonal close pack, each atom touches 12 others, which represents maximum packing efficiency. Higher coordination typically means stronger bonding and higher density, but it also depends on nature of the bonds. For ionic compounds, coordination is influenced by the ratio of ionic sizes. Large anions can only accommodate a certain number of cations around them. In nanomaterials, coordination changes dramatically at surfaces. Atoms on the surface have fewer neighbors than those in the bulk, leading to altered electronic structure and reactivity. Understanding coordination gives us insight into density, diffusion, and mechanical strength. To compare how efficiently different lattices use space, we define the atomic packing fraction or APF. It is simply the ratio of the volume actually occupied by atoms to the total volume of the unit cell. We treat atoms as hard spheres for this calculation. In simple cubic, only about 52% of the space is filled with atoms. The rest is empty. Body central cubic does better with 68% packing efficiency. The densest arrangements are FCC and HCP, each filling 74% of the space, which is the theoretical maximum for identical spheres. Why does this matter? Packing efficiency influences density, slip behavior, and thermal stability. For example, metals with FCC or HCP structures are generally denser and softer, while BCC metals often have lower density but higher strength. At the nanoscale, APF concepts help us understand surface reconstructions and nanoparticle morphologies, where packing can shift from bulk values. Let us start with the simplest lattice, the simple cubic structure. In a simple cubic cell, atoms sit only at 8 corners of a cube. Because each corner atom is shared among 8 neighboring cubes, the unit cell contains only one effective atom. The coordination number is 6. Each atom touches one neighbor along each Cartesian direction, packing is inefficient, which with an atomic packing factor of only 0.52, meaning that almost half the volume is empty space. Very few elements crystallize in this arrangement because of its instability. The best known example is polonium, which adopts this form at room temperature. While simple cubic is rare in nature, it is useful as a teaching model because it illustrates the fundamentals of coordination, packing, and unit cell calculations. It also serves as a contrast against denser structures like FCC and BCC, which dominate in real materials. In the body-centered cubic, that is BCC structure, atoms sit at all 8 corners plus one atom at the cube center. This addition greatly increases packing. Each corner atom contributes 1/8 of the unit cell and the center atom counts fully, giving a total of 2 atoms per cell. The coordination number is 8, which is higher than in simple cubic but not as high as in FCC. The atomic packing factor rises to about 0.68, making it significantly denser. Many technologically important metals adopt this structure: iron at room temperature, tungsten, molybdenum, and chromium. The geometry of BCC influences slip systems and hence mechanical strength. For example, BCC metals often exhibit high strength but lower ductility compared to FCC metals, especially at low temperatures. Understanding BCC is critical for metallurgy, nanostructures, and phase transformations like FCC to BCC change in iron, which underpins steel making. The face-centered cubic lattice, FCC, is one of the most efficient packing arrangements in nature. Atoms occupy the cube corners and the centers of each face. Each corner atom contributes 1/8. Each face atom contributes 1/2, yielding a total of 4 atoms per unit cell. The coordination number is 12, the maximum possible in 3 dimensions, and the atomic packing fraction is 0.74, which is the densest way to pack spheres in space. This structure is adopted by many metals including copper, aluminum, silver, and gold. FCC nanostructures are notable for their excellent ductility and toughness because of the high number of slip systems, close packed planes, and directions that allow dislocations to move easily. This makes FCC metals highly formable, suitable for wires, sheets, and complex shapes. At the nanoscale, FCC structures like gold nanoparticles often adopt truncated octahedral morphology reflecting the stability of close-packed 111 planes. Understanding FCC is essential in both traditional metallurgy and nanoscience. Now that we have learned the coordination numbers and the unit cell geometry of simple cubic, body-centered cubic, and face-centered cubic, let us derive the atomic packing fractions step by step, starting with simple cubic. To calculate atomic packing fraction, first count atoms in the unit cell. There are 8 corner atoms. Each corner contributes 1/8. That totals 1 atom per unit cell. Next, relate the atomic radius to the cube edge. In simple cubic, atoms touch along the edge, so 2 times the radius equals the edge length A. Now compute volumes. The volume of one atom is 4/3 times pi times the radius cubed. Because there is effectively one atom in the cell, the occupied volume is the same expression. The unit cell volume is A cubed. Substitute radius equal to A over 2 into the occupied volume. This simplifies to pi times A cubed divided by 6. Finally, divide the cell volume. The atomic packing fraction equals pi divided by 6, which is approximately 0.52. So, only about half of the unit cell volume is filled by atoms in the simple cubic lattice. Let us calculate the atomic packing fraction for the body-centered cubic BCC structure. First, we count atoms per cell. There are 8 corner atoms and each contributes 1/8 of an atom, giving a total of 1 atom. In addition, there is one complete atom at the body center. So altogether, we have 2 atoms per unit cell. Next, we establish the relation between the atomic radius and the cube edge. In BCC, atoms touch along the body diagonal, which passes from one corner through the center to the opposite corner. This diagonal equals 4 atomic radii. Geometrically, it also equals square root of 3 multiplied by the cube edge length. Now we calculate the occupied volume. 2 atoms multiplied by 4/3 pi times radius cubed. Substituting the radius as square root of 3 divided by 4 times the cube edge, we simplify the expression and obtain the occupied volume as pi times square root of 3 divided by 8 multiplied by a cubed. Dividing this by the unit cell volume, which is a cubed, gives an atomic packing fraction of about 0.68. Here, we will calculate the atomic packing fraction for the face central cubic or FCC structure. First, let us count atoms in the unit cell. The 8 corner atoms together contribute 1 atom in total. Each face atom is shared between 2 cells, so 6 faces add up to 3 atoms. Altogether, that makes 4 atoms per unit cell. Next, we determine the relation between the atomic radius and the cube edge. In FCC, atoms touch along the face diagonal. This diagonal spans 4 atomic radii. Geometrically, the face diagonal equals the square root of 2 multiplied by cube edge length. So we write 4r equals square root of 2 times a. Now the occupied volume is 4 atoms multiplied by 4/3 pi times radius cube. Substituting radius equals square root of 2 divided by 4 times a, we simplify to get occupied volume equal to pi times square root of 2 divided by 6 times a cube. The unit cell volume is a cubed. Dividing gives an atomic packing fraction equal to pi divided by 6 times square root of 2, which is about 0.74. This is the maximum possible packing fraction for equal spheres, and it is the same as in hexagonal close packing. Now that we have calculated the packing efficiency of simple cubic, body central cubic, and face central cubic, we saw that FCC gives us the highest atomic packing fraction of about 70.4%. That means only about 3/4 of the crystal volume is actually filled with atoms, while the rest remains as empty space. So the question is, what happens to this remaining 26% of space? Is 74% truly the absolute maximum packing any system can achieve? The answer is yes, but this limit holds only when all atoms are identical in size, like in pure metals. In real engineering materials, atoms are not always identical. When 2 or more types of atoms are present, as in alloys, the situation changes. The smaller atoms can occupy the empty spaces or interstitial sites left in packing of larger atoms. This allows us to increase the overall filling beyond the 74% limit of pure metals. In fact, this concept of multiple atoms sharing the same crystal lattice is what gives alloys their remarkable strength, density variation, and wide range of applications. To understand this better, let us revisit packing in 2 dimensions. The most efficient way to pack identical circles is the triangular arrangement, where each circle touches 6 neighbors. This arrangement corresponds to the hexagonal Bravais lattice. When we move to 3 dimensions, we add a second layer of spheres on the top of the first, with each sphere resting in the depressions of the first layer. Now, when we add the third layer, it can either align directly above the atoms in the first layer, or it can occupy a different set of positions marked as C. This leads to 2 possible stacking sequences. If the third layer goes directly above the first, we get an AB sequence, which forms the hexagonal close packed or HCP structure. Instead, the third layer goes into the C position. We get an ABC sequence, which gives rise to the face central cubic or FCC structure. Both have the same packing efficiency of 74%, which is the highest for equal spheres. Even at 74% packing, there are still empty spaces between atoms. These empty regions are called interstitial sites, and they come in two main types, octahedral and tetrahedral. Smaller atoms can sit in these sites without disturbing the main lattice too much. This is exactly how many alloys form. Small atoms like carbon in steel fit into the interstitial sites within an iron lattice. Let us now look at the relative sizes of interstitial holes. When atoms pack together, they leave specific cavities where smaller atoms may fit. The size of these cavities can be expressed in terms of the host atom's radius r. In a tetrahedral hole, which is surrounded by 4 atoms arranged like the corner of a tetrahedron, the maximum radius of the atom that can fit is about 0.225 times r. This means the interstitial atom can be less than a quarter the size of the host atom. In an octahedral hole, surrounded by 6 atoms in an octahedral geometry, the cavity is larger. The maximum radius of an atom that can fit here is about 0.414 times r, roughly 40% of the host atom's radius. These values are key for predicting which elements can occupy interstitial positions in crystalline materials. Now let us connect interstitial sites to the concept of alloys. Alloys are a combination of 2 or more elements, and they can form in 2 distinct ways. In substitutional alloys, the atoms of one element directly replace some of the host atoms in the lattice. A classic example is copper and zinc forming brass. In interstitial alloys, smaller atoms squeeze into the tetrahedral or octahedral holes of the lattice without replacing the host atoms. One of the most important examples is carbon in iron. Carbon atoms fit into octahedral sites in the iron lattice, creating steel, a material with far greater strength and versatility than pure iron. Other small atoms such as hydrogen, boron, nitrogen, and oxygen can also occupy these interstitial sites in different metals, producing compounds with unique hardness, magnetic behavior, or catalytic properties. This interplay between lattice geometry and interstitial filling explains why alloys are so technologically valuable. Now, once we have learned how atoms are stacked together to form closest packed solids, let us see what is the smallest possible FCC particle that is structurally stable. The answer is a 13 atom cluster. It has 1 atom at the center, 6 atoms in the same plane, 3 above and 3 below. This symmetric arrangement provides the best geometrical stability for such a small nanoparticle. The next stable particle appears at 55 atoms. This is formed by adding 42 atoms around the original 13 atom cluster. While preserving the same symmetric arrangement, such clusters are geometrically favored, giving rise to the next magic number, and they serve as the building blocks for larger, stable nanoparticles. Now that we have seen the stability of the 13 atom and 55 atom clusters, we can generalize this idea to larger nanoparticles. Each time a new symmetric shell is completed around the previous cluster, another stable size appears. These spatial cluster sizes are called structural magic numbers. They arise directly from the geometric stability of FCC close packing. After 13 and 55 atoms, the next stable sizes are 147, 309 and so on. Each of these corresponds to a complete symmetric shell, giving the nanoparticle enhanced stability compared to other sizes in between. In this table, we can clearly see the sequence of structural magic numbers starting from 13 atoms, then 55, 147, 309, and so on. Each of these corresponds to a fully closed shell in FCC packing, where the particle achieves geometric stability. Notice also the fraction of atoms on the surface, more than 90% for very small clusters, gradually decreasing as the particle size grows. This trend highlights why small nanoparticles are dominated by surface effects, while larger ones behave more like bulk materials. To summarize, we learned how the atomic packing fraction varies for different cubic structures, with FCC and HCP giving the maximum packing efficiency of about 74%. The unfilled spaces in these packings create interstitial sites, tetrahedral and octahedral, which play a critical role in alloys. By occupying these sites, atoms like carbon, hydrogen, or nitrogen allow alloy to achieve higher effective packing. Finally, we introduced structural magic numbers such as 13, 55, 147, and 309, which describe particularly stable clusters formed due to the geometrical considerations. These concepts lay the foundation for understanding both bulk metals and nanoparticles.